An example of the resolution of two different telescopes is shown here. You see two images of Pluto and its moon Charon. The Earth-based telescope cannot resolve the two objects, but the Hubble telescope can distinguish them easily. The Hubble telescope is diffraction limited because its angular resolution is only set by the ratio of the wavelength of the light to the diameter of its primary mirror. Earth-based telescopes aren't ever going to be diffraction limited, and the main reason is Earth's atmosphere scattering the starlight and spreading out the images. The Hubble telescope's quality is taken for granted now, but in fact, soon after it was launched, they discovered that the main mirror had been polished incorrectly and it was too flat at the edges. This optical defect meant that the telescope could not produce diffraction-limited performance. A large-scale project was put in place to find the exact problem and then design corrective optics. A mission was launched to put those extra optics in front of the telescope, essentially acting as a pair of glasses. Finally, they could get clear images. You can see at the bottom before and after images of Galaxy M100. Radio waves have a large wavelength, and then from the condition that the Rayleigh angle is 1.22 lambda over d, the bigger lambda is, the bigger the minimum angle. So radio telescopes battle with the problem of poor resolution. Now, the simplest way to improve the resolution of a radio telescope is to make it as large as possible. But in fact, what they now do to increase the collecting area, the radio telescopes are made in the form of arrays. So in an array, two or more telescopes are used together and their signals are combined with computers. The distance between two telescopes can be large. You may have heard about the plans to build the square kilometre array of radio telescopes. Using all of those with their signals combined together would be equivalent to a single radio telescope with a diameter of a kilometre. Now, as an exercise, we're going to find the angular resolution of the Parkes radio telescope, which has a 64-metre diameter, observing radio wavelengths of 5 centimetres. Now, for the Parkes telescope, we have a diameter of 64 metres, and the wavelength we are interested in is 5 centimetres, which is 5 by 10 to the minus 2 metres. Now, the minimum angle that it can resolve is 1.22 lambda over d from Rayleigh's criterion, which is 1.22 times 5 by 10 to the minus 2 over 64, and that is 9.5 by 10 to the minus 4 radians.